Hello and welcome to 15.1 Explaining Equilibrium Systems or equations. So basically the first little bit, we're just going to familiarize ourselves with some definitions. And then towards the end of the 15.1, the first half, we're going to take a look at an example of what an ice table is. So first of all, a chemical system that is separate from its surroundings where no matter can enter or leave is called a closed system. It's important for equilibrium systems that it's a closed system, meaning products can't escape and reactants can't escape. When a bottle of carbonated beverage, as an example, is opened, the pressure on the system changes and the dissolved gas is allowed to leave the system. When it's closed, kiddos, when this bottle is closed, it's a closed system. The moment you open it up, it's an open system and equilibrium has been disturbed. So what is equilibrium? We're going to take a look at that. Closed systems at equilibrium. Evidence for many chemical reactions occurring in a closed system has shown us that after some reactions appear to have stopped, there is a mixture of reactants and products that are present. So you kind of looked at this in Chem 20 when we were looking at saturated solutions, where the products being formed, crystallization, and the products being turned back into their ions, ionization or dissociation is equal, and there's two arrows, one pointing in one direction, one in the other. That's what we're talking about with equilibrium systems, okay? There's a forward reaction and a reverse reaction. So what this means is that even though these products are being formed, it actually goes back to the reactants. There's a back and forth, and equilibrium means that it reached a point where it's equal as it can be. So evidence for many chemical reactions occurring in a closed system has shown that after some reactions appear to have stopped, there is a mixture of reactants and products. And here we go. There's always going to be reactants and products, assuming that it's not only a forward reaction. We'll talk about that in a bit. We assume that any closed system with no observable changes occurring is in a state of dynamic equilibrium. This is from Chem 20. Dynamic means changing always, so one direction to the next. Equilibrium, that means it's about equal. So it doesn't change. The amount in there doesn't change. It's just going back and forth all the time. This dynamic is this movement of products to reactants, reactants to products, products to reactants. Equilibrium just means that at some point the concentrations of the reactants and the products don't change. The forward reaction, also known as the collisions between reactants to form products, and the reverse reaction, you can think of that as collisions between products to form reactants, are occurring simultaneously and at the same rate. So they're happening at the same time and at the same rate. And that's dynamic equilibrium, kiddos. So equilibrium occurs when a reaction can go in either direction. The majority of reactions can be equilibrium situations. Some are not. Some can only go in one direction. There are three main types of equilibria. I'm not testing you on this. This is just some information. Phase equilibrium occurs between the phases of a substance. Phases, you guys remember what that means? It's going from like gas to liquid, liquid to gas, liquid to solid, solid to liquid, and you can even go solid to gas, gas to solid, sublimation, right? As a water molecule evaporates, there's an example. Another molecule of water vapor condenses. The rate of the evaporation reaction equals the rate of condensation reaction. The reactants are at equilibrium. Remember, phase change is in that weird area where things are kind of in the middle. Like the freezing point of water and the melting point of water are both at 0 degrees Celsius. So you get this funky slush. You don't get, it's not quite frozen, but it's definitely not quite liquid. It's not a liquid or a solid. It's in that phase of like in between. Melting point 0, freezing point 0 of water, you get kind of a slushy. That's phase, that's an example of phase equilibrium. Here you have an example of just going from, in this case, from gas to liquid. So solution equilibrium is a different type of equilibria. It occurs when a soluble non-volatile substance is dissolved in a solvent. This we learned about in Chem 20. If the solution is saturated and there is still solid solute at the bottom of the beaker, the system is at equilibrium. So here, if you can take a look, it has this double arrows. So the copper 2 sulfate solid is being dissociated into its ions, but also the ions are crystallizing into the solid. And it's happening at the same rate and at the same time. So you have this phase, well, it's not even a phase, correct that. It's this situation where it's saturated. It's like products are being formed and the product is ionizing back at the same rate. Chemical equilibrium, this is what we're going to do moving forward in this whole unit, occurs in a chemical reaction system. Phase and solution examples are physical reactions only, right? So those two examples are physical changes or physical reactions. We're going to spend our time with chemical equilibrium or chemical reactions. So let's take a look at an example of what that looks like. I have hydrogen gas plus iodine gas, and it's going to create hydrogen iodide. Okay, or hydrogen monoiodide to be more specific. Take a look over here. It's showing you that it's equilibrium, so the products are being formed, but they're also going back into their reactants. And this occurs at 448 degrees Celsius. So let's take a look and break it down as to what is going on, just so you can have a representation, a drawing representation. So initially, hydrogen happens to be in excess and iodine are added to the flask. The color of the iodine vapor is the only easily observable property, so it's quite dark. This just tells you that in the very beginning, all you have are the reactants, the I2 gas and the H2 gas. So it's quite dark purple. This is just a physical observation that there's a lot of reactants. So as these two are added, at some point they're going to start reacting. As they start reacting, you'll see that all of a sudden you have a new player, and that's your product, right? So as these two react, they form a product. All of a sudden the color changes because now the two reactants are actually decreasing in concentration and the product is slowly increasing in concentration because those reactants are reacting to form a product, whereas before here, there's just the reactants, okay? So early in the reaction, hydrogen and iodine form hydrogen iodide faster than hydrogen iodide forms hydrogen and iodine. Overall, the amount of iodine decreases, so the color of the flask contents appears to lighten. Both hydrogen and hydrogen iodide are colorless, so we only take a look at the iodine presence. So at some point, this stops in terms of only creating a product. At some point, you reach equilibrium where you have the double arrows, where remember it's happening at the same time and at the same amount at the same rate. At equilibrium, analysis shows that the flask contains all three substances, okay? And now at equilibrium, the concentrations of the substances remain constant. They don't increase or decrease, they're constant. However, they're still going back and forth between reactants and products. The purple color shows that some iodine remains. Obviously, there are some reactants. The constancy of the color is evidence that equilibrium exists. So once this color remains and doesn't change to darker or lighter, we've reached equilibrium. That's just a physical representation of that. Forward and reverse reactions are occurring at equal rates. So now we have dynamic equilibrium. So this is just, this kind of evidence is just what scientists use or chemists use to say, hey, what's going on? What's this concept? What is this concept? So let's take a look at plotting some numbers. So let's take a look at this first system where you only have reactants in a flask, for example, and nothing has been done yet. You're starting off with the reactants. This is your initial system concentrations. So we just added hydrogen, we just added iodine, and it happens to be that we added 5 millimoles per liter of each. At the very, very beginning, there's no product. This is before the reaction occurred. At equilibrium, okay, you'll notice that the 5 went to 1.1 and this 5 went to 1.1 because those are decreasing because now they're reacting to form the product. So the product amount increased from 0 to 7.80. Here's just another example where you have a mixture of reactants and products. So in this case, number 2, we have, to start off, 0.50 millimoles per liter of hydrogen, 0.50 millimoles per liter of your iodine, and already you start off with the 1.70 millimoles of the product. At equilibrium, it still shifts. So in this case here, it still decreases, and increases, okay? And if you take a look at the third example, you're just given a product, okay? So you're starting off with just a product. Because it does reach equilibrium, what's going to happen is this is going to decrease, right? And these are going to increase because they started off at 0. And there we have the data. This increases and the product decreases because of this double arrow, showing that products also go back into reactants. No matter the starting conditions, the system reaches a state of dynamic equilibrium each time. And it's evidence like this that came up with the concept that allowed chemists to come up with the concept of this. So how does that look like in a graph? In a graph, you could take a look at the fact that in the very beginning, if you add just your reactants, they start off quite high, right? And then they decrease. They decrease because they're being used up. Here, at this stage here, this is where the reaction is taking place. When the line goes straight, or it's parallel to the x-axis, this is equilibrium, okay? So equilibrium has come to like the state of equilibrium when the line is pretty much parallel to the x-axis. So reactants of hydrogen and iodine start high, but as the reaction occurs, they decrease, which makes sense. Your product starts off at 0 because at the very beginning you just have the reactants, and as the reaction occurs, the product increases, which makes sense. So the rate of the forward reaction decreases as the number of reactant molecules decreases. There's fewer collisions. And the rate of the reverse reaction increases as the number of product molecules increases. So this is really, really important, kids. As you increase the product, okay, it actually reverses. So it goes back to the reactant. Does that make sense? And the rate of the forward reaction decreases as you get more and more products. The forward reaction will decrease as the number of the reactant molecules decreases. So there's this back and forth saying at the very beginning, it was making a lot of product. At some point, the product is like, I'm good now. So then it shifts back to the reactants to get this equilibrium. Dynamic equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction and then at that point, you'll notice it's a straight line, no curve. So 5 conditions are necessary for equilibrium to occur, kiddos. The reaction must be reversible, obviously. The system must be closed. If you have an open system, you can't keep the reactants of the products in one place. It's hard to tell what the heck is going on. Both reactant and product must be present, obviously. Concentrations of the reactant and the product do not change. You're not adding extra reactants as the equation is occurring or as the reaction is occurring, and you're not adding or taking away product. Everything is constant. You're not changing anything. Another thing to keep in mind as well is that conditions of temperature and pressure must be held constant. You guys remember from Chem 20, as temperature increases, if you're dealing with gases, the solubility of gases decreases. So you don't want to mess around with the temperature and the pressure because that's going to give you false readings or false data. So percent reaction or percent yield, remember that from Chem 20, is the yield of product measured at equilibrium compared with the maximum possible. So the maximum possible yield is 100%, but we all know that that's like really, really impossible unless you have your reactants to be 100% pure and everything is like tickety-boo. Maximum possible yield is calculated using STOIC. Stoichiometry assumes no reverse reaction possible. In other words, it assumes the reaction runs 100% complete. You can only use STOIC, kids, only when it's not a reverse reaction. Only when it moves a forward reaction. An example of that is a hydrocarbon combustion reaction. If I take methane and I react it with oxygen and it burns to create carbon dioxide and water, it's not going back. You cannot reverse that reaction back to methane. Can you imagine if you could do that? That would be awesome. We would have no issues with using fuel because it would go back, but it doesn't. It produces carbon dioxide and water. That's it. That's all. It does not go back. So that's one example of a reaction that does not get to equilibrium. It's only a forward reaction. So this means that 100% of the product would be produced and no reverse reaction. There's no reverse reaction. Hydrocarbon combustion is the example like I talked about. So yield of product, or the actual yield, is achieved by experimentation. So percent reaction is equal to the actual yield over your theoretical yield or your maximum yield. times 100%. When we communicate percent reaction, we write the percentage above the equilibrium arrow. So even though it's quite high, so what this is telling you is that most of the reactants are going to become products, only 78%, which means that there's a little bit left over that are reactants, right? That it's 100% minus 28%. Sorry, 100% subtract 78% is going to give you the percentage of the reactants that are going to be always around at equilibrium. This is quite high, but it's still not 100. So it's still not just a forward reaction. That's why we have the double arrows. So let's talk a little bit more about percent yield. 78% of this just tells you that, listen guys, if I'm reacting hydrogen and iodine, 78% of that is going to turn into hydrogen iodide, okay? But there's still some of the products going to be shifting back to the reactants, just not that many. So this means that 78% of the reactant molecules have formed product molecules. Now here's the thing, this is at equilibrium. So this just happens to be that specific amount for that specific equation. That can change. It could be 50%. Very rarely is it exactly 50%. It could be 89%. It could be 32%. If it's a 32% yield, that means that only 32% of there's only 32% probability that the reactants are going to change into products. So this is arbitrary. This doesn't matter. This is just forming just giving you some detailed information about how much of the product is going to be formed, but it's still dynamic equilibrium. So at equilibrium, there are more product molecules that have been formed than reactant molecules that are left over. That's okay. And that changes depending on what you're looking at. So let's interpret percent reaction. If the percent reaction is a less than 50%, then this is just a different way to articulate. Reactants are favored. This is a really important word because now with equilibrium we use the word favored. What's being favored, the products or the reactants? If the little number above the two arrows is less than 50%, right? Then the reactants are being favored. There's always going to be more reactants than products. If the percent reaction is higher than 50%, then the products are favored. Okay, and what that means is that a large amount of products is produced and a small amount of reactants are left over, even at equilibrium. So at equilibrium, if the percentage is higher than 50%, products are favored. At equilibrium, if the products are less than 50%, the reactants are favored. If the percent reaction is about 99%, then it is quantitative. Then there's only one arrow, kiddos, and it's the forward reaction. This means that only products are found at the end of the reaction. For reactions that are 99% or greater, we do not use the double arrow system. Instead, we use a single arrow system, saying that, listen, this equation here only produces products, like a hydrocarbon combustion reaction. There ain't no way, no how, it's going back to the original hydrocarbon or the fuel, which is a shame. So here's an example, just in a table form. Reactants are favored. You still have the double arrow, and it's going to be less than 50%. If the products are favored, you're still going to have a double arrow. It's still equilibrium. It's just that the percentage is going to be higher than 50% when the products are favored. If it's quantitative, kiddos, which is so perfect, so much easier. You don't have to do any ICE tables. You just have to do ICE tables. What's that? We're going to learn in a bit. You just have to do stoich, which is obviously our favorite. And if that's the case, you only have one arrow, and it's showing the forward reaction. So back to that initial thinking about what's going on with the hydrogen iodide system. Here we have, remember, we started off with only your reactants, and then the reactant concentration goes down because the product concentration goes up. And it's not 50-50. You can see by the numbers. This did not go down 50%, and this did not go up 50%. It went up a lot higher. Remember, 78%, it was a 78% product or percent yield. And then we also looked at a mixture, right, of reactants and products. Is still going to start to shift, and the reactants are still going down, and the products are still going up because it's the 78% yield. And if you start off with no reactants, only the product, the reactants are going to go up and the product is going to go down. That makes total sense. And in this, if you take a look at equilibrium, it's just showing where the 78% came from. No matter what you started off with in terms of concentration, at equilibrium, there was always a shift, right, to always get you 78%-ish yield, and that's where that data came from. The maximum possible yield is calculated using Stoich, assuming all of the reactant molecules are used up to form the products. So there's something called ice tables. I'm going to show you one example of a very simple ice table. And in part 2 of this, we'll look at more complex ice tables. But for right now, just very simple ice tables. An ice table or ice tables are used for quantitative calculations. So we're using an ice table for quantitative, right, calculations involving chemical equilibrium systems that are not quantitative. So they're not higher than 99%, they're actually less than 99%. So there means that there's that double arrow. We have to use ice tables. And most of the times, this is what happens. Very rarely, not a lot of examples go just to the forward reaction. Ice stands for three things: the initial concentration of each entity of the equation, the change in concentration, does it go up, does it go down, and the equilibrium concentration. After these stopped reacting, after they're done, they're not, the concentrations of the reactants and the products are not going to change. You reach equilibrium concentration, okay? An ice table describes what happens to the concentrations of the system as it reaches equilibrium or reestablishes equilibrium. And we're looking at the ice table, you're looking at the reactants and the products and how they affect each other. So here's an example. You have any general reaction. Entity A plus entity B is going to yield entity Z. Now here, this changes. This is just an example. You can actually have 4 species. You can have reactant, reactant yields product, product. You can have reactant, reactant, reactant yields product. So this is just an example, but the way it works is always the same. So when you're labeling your rows, okay, it's always your ice table. Your first row is always your initial concentration of the reactants and products. Your second actual row of the data collecting is your change in concentration. And the last row is always your equilibrium concentration of everything. How do you label your columns? Each column represents each entity of the equation. So you have entity A, entity B, and entity Z, because each of them are going to change. You're going to have initial reaction for each of them, and you're going to have a change in concentration for each of them, and then you're going to have an equilibrium for each of them. Just a little note, your change in concentration is equal to your concentration of equilibrium, right? Subtract your initial concentration. And just so you know that your equilibrium concentration is just your initial concentration plus your change in concentration is going to get. So if I take these two and add them up, it's actually going to give me my equilibrium concentration. So let's see what this looks like. All right, so here's an example. I love the grammar of your textbook. So consider the reaction equation for the formation of hydrogen iodide at 448 degrees Celsius. Assume the reaction is begun with, love it, 1.00 millimoles per liter. Now words like begun with, okay, is begun with implies initial concentration. Concentrations of both H2 and I2 gas. So each of H2 and I2 gas begins with a initial concentration of 1.00 millimoles per liter. Construct a nice table to determine the equilibrium concentration of the reagents. The equilibrium concentration of I2, they're just giving you the equilibrium concentration of I2 is 0.22 millimoles per liter. So it's important that you take a look at your question and you start unpacking it, start breaking it down, underlining the information that you need, because you have to construct a ice table and add all that data, populate your ice table. So I'm going to start with my ice table. Initial concentration, change in concentration, and equilibrium concentration. These are the entities of your reaction, right? So you have reactant, reactant, product, okay? So then you're going to start populating it. You know that you started off with the question telling you that 1.0 millimoles per liter for each of the reactants. Now, they didn't tell you, they didn't give you the initial concentration of the product, so you have to assume it started off as 0. You have to assume that because they only give you the initial concentrations of the reactants, both reactants and not the products, we make the assumption that the products haven't started forming yet. So we have to give it a value of 0.00. And you were also given the value of the equilibrium concentration of only iodine. So we have to plot this. So now we have to use some simple math to figure out how to do the rest, but it's pretty cool. Next, calculate the change, the decrease in concentration of the iodide. So we take the 0.22 minus the 1, because that's the only place we can do that, only for the iodine, and that gives you 0.78 millimoles per liter. Once you have this concentration, okay, right? Once you have this concentration, then we use molar ratio to find the concentration of the rest. So the changes for the other concentrations can be achieved by using molar ratios. Stoic again, love it. I love it. So when you're talking about change in concentrations, that's the only place you can use stoic. Okay? So once I have one of them, I can definitely use my molar ratios to find the rest. So, for example, for hydrogen, the change is also a decrease, a negative value, because you are decreasing your reactants. Your reactants are going up, down, pardon me, and your products are going to go up. So for hydrogen, the change is also a decrease, so we give it a negative value. And for hydrogen iodide, the change is an increase, a positive value. So we take the 0.78 millimoles per liter and you multiply it by 2/1, because when it's balanced, it's 2 moles of the hydrogen iodide for each 1 mole of your iodine. Okay, kiddos? And it's positive because that's being produced. And these are negative values because they are being consumed. Okay, and I have that here. I've articulated that for you. The change in concentration of reactants is negative because they are being consumed. It's positive for the products because they are being produced. This is super important that you add those negatives and positives. Once that's done, right, to find the equilibrium concentration after equilibrium has been reached, use your simple formula of initial concentration plus change in concentration, and then you get your equilibrium concentration. And that's why it's really important, kiddos, that you include those negatives and positives. If the reactants are being consumed, you have to give it a negative value. If the products are being produced, you have to give it a positive value. And that's it for now. That's ICE tables in a nutshell. This is the end of your part 1 of the 15.1. Have a great day, kiddos.